we talked about some basic properties for addition and scalar multiplication, and we talked about a little bit of algebra involved in there. And so here we're looking at matrix multiplication and taking a look at properties for matrix multiplication, and then we'll take a look at some algebra here. And in this particular section, we're going to get stuck on trying to solve for one of those algebraic equations that we have for these matrices, and then we'll see how to uncover that in the next section. So we had the addition and scalar multiplication properties last time. We talked about the scalar multiplication, or we talked about the addition being commutative. We can add a plus b and b plus a will give us the same result. So that's one of the big results for multiplication, and the multiplication is not commutative. But it is associative, it is distributive in both ways. And remember, we have to consider both ways now because of the fact that it's not commutative. So multiplying from the front is different as multiplying from the back, or multiplying from the left is different as multiplying from the right. Scalar multiplication is also associative if we could decide to do the scalar multiplication first, or we can decide to multiply the vectors first, or the matrices first. But here's another interesting thing, is that that scalar multiplication for a product of matrices can go either on the first matrix or the second matrix before you multiply it. So that is an interesting property that still doesn't bother the commutativity of matrices, or lack thereof. And then here is your identity matrix times A. This is the, sometimes it's called the multiplicative identity. Just like the additive identity was discussed. So in the previous lecture, we talked about some basic algebra and solving for equations that involve matrices. And so one of the important equations we have is well, not one, but so this is equation for the next section. Is that if we have a matrix multiplied by some unknown matrix that we're solving for, we want to know when this is going to equal to the identity matrix. And the way we would solve for this if it was just real numbers is that we would say, this is a 3x is equal to 1, we would just divide by 3, right? Divide by 3, so x is equal to 1/3. So we don't have a division for matrices, so the idea of dividing is a little bit different. And so this is when we're going to introduce the multiplicative inverse. So in addition, we have what's called the additive inverse. That's just a minus in front of the matrix. But the multiplicative inverse is going to be a little bit more challenging. We'll do that before the end of today. All right. So these are the general properties. Let's take a look at some problems that we might run into in our homework or somewhere else. Here are some interesting problems. Find conditions for A, B, and C, and D. that make these this matrix multiplication commutative. So because multiplication is not commutative, sometimes there is some special matrices or special pairs of matrices where it might commute. So let's do one of these, A, B, or 23, 24, 25. Which one should we do? Any guess? Any Let's do 25. So the question is, we want the product to be commutative, and so what special numbers A, B, C, D can we put into this matrix so that they're actually commutative? So what we want to do is essentially try to work out both sides, and then we'll see if we can find parameters or find conditions for these values A, B, C, and D so that it would work out. So let's do A, B first, and this is our A matrix 1, 2, 3, 4, and your B matrix is A, B, C, D. So this product is going to be, how's that song go? What? Row times column. Yeah, you weren't here earlier. So 1 times A, 2 times C, so A plus 2C. 1 times B, 2 times D, so it's B plus 2D. And then row and column, so 3A plus 4C and 3B plus 4D. So that's a product one way. Let's figure out the product the other way. Now let's keep it blue. And so now instead of multiplying by A first, let's multiply by B first. So A, B, C, D, and then 1, 2, 3, 4. So row and column, that would be A plus 3B, 2A plus 4B, C plus 3D, and then 2C plus 4D. All right. Now we got a big mess here, but let's see what we can do. And if AB were to equal BA, then we better have the first components equal to each other, and the second components equal to each other. And I'm calling them components, but you know, the third. Now it's confusing. The fourth. Too much? Okay. Let's just start with this. So essentially what we're going to have is a, guess what? A system of linear equations. A plus 2C equals A plus 3B, and then B plus 2D equals 2A plus 4B, 3A plus 4C equals C plus 3D, and then 2C, or let's call it 3B, plus 4D equals 2C plus 4D. Right? Looks like a big mess right now, but essentially you have 4 equations and 4 unknowns, and they're all linear, so it's really just a set of linear equations. We could solve for it any way we want, but first let's bring everything over to one side and set it equal to 0 so it looks nice. It looks like if we bring everything to one side, the A's would cancel, so I'll have negative 3B plus 2C equal to 0, and I'm leaving some space for the variables A and D. Bring everything to the left side. I have negative 2A plus B, no C's, and then minus 2, negative 3B, right? So negative 2a, bring the b's over, so negative 3b, no c's, and then positive 2d. And we have a 3a, no b's, plus 3c, minus 3d. And then finally, there's no a's for this one. We have 3b minus 2c, and the d's are gone. So you get a nice system that looks like this. We just have to find solutions for A, B, and C, D. You know, I'm going to use Wolfram for this, right? Because you guys know how to do this already. Or do you? Oh, come on. 0 minus 3, 2, 0. And the augmented part is 0. Minus 2, minus 3, 0, 2. 3, 3. Oops, there's no B. 3, 0, 3, and negative 3. 0, 3, minus 2, 0. All right, so I don't have a 1 in my first slot, so I might want to do a little swapping first. I'm going to take this, why don't I take this row here and move it up to the top. So I'm going to take row 3 and then first replace it with 1/3 row 3 and then move row 3 up, swap it with row 1. So I'll divide out the 3 and then move that up in the first slot, or in the first row. 1, 0, 1, negative 1, 0. And then I swapped this one down. So 0, minus 3, 2, 0. Going to be a long page here. All right, what can we do? Maybe we need to wipe this 2 out, or negative 2. So I'll take row 1, multiply that by 2, positive 2, and add that to row 2. So 1, 0, 1, negative 1, 0. I'm going to write smaller so I can fit more matrices here. Got rid of that. This stays negative 3. 2 times 1 is 2, plus 0 is 2. Negative 2 added to this positive 2, and that's going to be 0, and then that's 0. Wow, so it looks like I can, all the signs here, so I can wipe out a couple of rows here, right? So whatever, whatever. So I'm going to keep this as negative 3, 2, 0. And then whatever row reducing you need to do to make these equal to 0. I'll get rid of those. So it looks like my row reduced here looks like this. I can make this negative 3 into a positive 1, but I'll just leave it as negative 3. And so this tells me, what does this tell me? How many free variables should I have? I should have two free variables, right? So maybe I'll let my D equal to one free variable and my C equal to the other free variable. So we got a couple of free variables, and once we know that D is equal to S and C is equal to T, free variables, then I can figure out what my A and B are equal to. So according to the second row, I have minus 3B plus 2C is equal to 0. So minus 3B is equal to negative 2C, and C is equal to T. So B is equal to 2/3 of T. And then the last one says that A is equal to, I'll say A plus C minus D is equal to 0. So A is equal to D minus C. So I'll write the C first. So negative C, which is T, plus D, which is S. So this isn't quite clear enough, so I would write it as A, B, C, D is equal to something with an S and something with a T. All right? So if I start from the bottom, which is where I started from over here, I have S. D is equal to S. So there's no T's there, and that's just one S. So one S and then 0 for T for D. So C is a T value. B is 2/3 of T. So 2/3 of T with no S values. And then A is negative T plus S plus 1S. So negative 1T plus 1S. So the combination of A, B, C, D values that would satisfy this equation would give us some values for that matrix. This is really getting long, this paper. Should have gone to the next page a long time ago. Oh well. What does that mean? That means some examples of such matrices would be maybe if we let S equal to 1 and T equal to, I was going to say 0, but let's let T equal to 3. Then your matrix might look like this. So A will be 1 times 1, S is 1, right? And then T is equal to 3. So this would be 1 minus 3, negative 2. S is 1, so that's 0. T is 3 times 2/3, that's 2. So that's what B is equal to. C would be 0 plus 3, right? When T is equal to 3, S is equal to 1, T is equal to 3. And then the last one, S is equal to 1, T is equal to 3, but it's multiplied by 0 anyways. So this thing, when you multiply this by 1, 2, 3, 4 on either side, should equal to each other. Okay? That's what that means. Does that make sense? Should we check? I'm just going to check real quick. it should be still the same, should be equal. This is on another screen. It's not popping up in my main screen. Anybody know how I can get it back here? Oh, I know. There you go. Bam, magic. So A is 1, 2, 3, 4. And we said for this particular example that we're checking, B was -2, +2, 3, 1. So if I multiply A times B and B times A, should be equal, right? And in fact it is. So that's all. So we could find different values for S and T that would give us our different values where we multiply the matrices in reverse order. We should get the same thing. That was a fun exercise. Yeah. Would say that not S and T, because S and T were the parameters. You would say that, what would you say? No, you would say that these two vectors are linear combinations of each other. And then that's how you would find your A, B, C, D. So you could say that A, B, C, D, those components of the matrix, is a linear combination of these two vectors. Or these two matrices, if you want to put it as a matrix. Oh, in fact, well, why don't we do that? So any linear combination of 1, 0, 0, 1, oh, that's the identity matrix, and -1, 2/3, 1, 0. So any linear combination of this means if you scalar multiply this and add them together, that would satisfy this commutative property for this particular matrix. Okay? So thanks for bringing up this linear combination idea, because it kind of fits in this discussion. And you know where I got these matrices from, right? All right, moving on. Each of these problems takes so long. Okay, here's another one. 26 is kind of similar, but we don't have time to do that. Let's move on to another matrix operation called a transpose. Did we do the transpose already? Did we do this already? I feel like I'm having deja vu. Yeah, deja vu in the matrix. That cat that came in, there's a glitch in the program. Yeah, never mind. Transpose, switching rows and columns. So a couple of important properties for the transpose. If you take the transpose of a matrix and then take the transpose again, you get the original matrix back. That kind of makes sense, right? You switch rows and columns, and you switch rows and columns again, you get the original matrix. If you add a couple of matrices and then take the transpose of them, it's like taking the transpose first and then adding them. That's an important property. It looks like you're distributing the transpose over the addition. That's kind of interesting. Because if you look at property D, it's distributing the transpose over the multiplication. But there's something weird happening there. We'll get there in a minute. Taking the transpose of a scalar multiple of a matrix is like taking the scalar multiple out first and then taking the transpose of just the matrix. That's that thing. This is the one that I wanted to point out that's kind of weird. Taking the transpose of a product is like taking the product of the transpose, but look at A and B and B and A, right? Remember that multiplication is not commutative, so whenever we deal with products, we always have to be careful about identifying which one comes first. So if you take the transpose of a product, it's like taking the product of the transpose, but you're reversing the order of the multiplication. Okay? So the proof of that is it's a little bit more difficult than we have time for, but you can take a look at the proof in the book. If you don't want to look at the proof in the book, then you just have to take this for what it says, and so you just have to believe it. The other one is the product. Well, it's not a product, it's a power, but remember what power is, right? Power is just multiplication of things. So imagine a to the third. You want the transpose of this. This is equal to, according to this, well, let's break it up into a times a squared first. This is equal to, according to property D, this is equal to the second matrix transpose times the first matrix transpose. But since these two are the same, A and A squared is just A times A, that, in that case, you can actually just use this property here. What? Yeah, so this is A times A transpose, which is equal to A transpose times A transpose. So this is essentially A transpose times A transpose times A transpose, which is A transpose multiplied by itself 3 times. So we have been living in this world of real numbers where real numbers are commutative, and so we take a lot of these things for granted. And so here's a case where it looks like I could just switch a transpose into power, but switching the transpose into power relies a little bit more on some of the theory behind this. So be careful when you're multiplying a couple of things, you're finding the transpose of them. Couple of theorems that follow from the properties. If A is a square matrix, then A plus A transpose is a symmetric matrix. That's an interesting thing to prove. And then for any matrix A times A transpose and A transpose times A is symmetric matrices. So we studied, in the study, we defined symmetric matrices via the problems from the previous section. So this is one of those things in linear algebra where these properties are really important, and really like to do a bunch of examples of them, but we don't have time because we need to move on. And when we do come up with this, we're going to bump heads with these properties again later on. We'll just try to re-highlight them and say, do you guys remember back when? And then you guys are going to say no. Yeah, so. Okay. All right, a couple of more definitions. There's so much material that they didn't want to fit this into the regular discussion of the book and the text, so they decided to put this in the problems. Square matrix is called skew symmetric if the transpose is equal to the negative of this. This is a simple check. Let's talk about skew symmetric matrices. And we may do one of these two proofs. Which of the following are skew symmetric? So what do we want to do to check if it's skew symmetric? We take the transpose, right, and it would compare it to the negative of A. So let's take a look at problem A here. So A transpose, what's a transpose of this? I write things row first, then go down and go across the row. So what's a transpose of 1, 2, negative 2, 3? What? 1, negative 2, 2, and 3. That's a transpose of this, right? What's minus A? So I take this and just put negative signs in front of the whole thing. So minus 1, minus 2, positive 2, negative 3. Are these two equal? No, they're not. So A is not skew symmetric. Let's take a look at B. What's the transpose of B? 0, 1, negative 1, 0. And what's the negative of this matrix? 0, 1, negative 1, 0. Are these two equal? Yes. So yes, this is skew symmetric. All right, so that's how you would check if something's skew symmetric. Which one do we want to do? 38 or 39? One of them is a proof. The other one is kind of like a proof. Let's do one of them just for fun. 39? Yeah, you guys are going to go for the proof, right? Prove that the main diagonal of a skew symmetric matrix must consist entirely of zeros. So for a proof like this, to try to prove this, let me cross that one out just so we don't mess with it. Let's see if we could prove this. Because in this particular proof, what we want to do is we want to show that all the whole diagonal must be equal to 0. This is a prime candidate for what's called proof by contradiction. And contradiction means, what if we assume that the whole diagonal is not exactly 0? Okay, that seems like a good first step for this. And then what should happen is that I should come up with something wrong, right? A contradiction. So we're going to do this proof by contradiction. Assume, when you do a proof by contradiction, you're going to assume something that isn't supposed to happen. Okay, so here in this case, we're going to assume that the diagonal is not all 0. So if we're going to assume that the diagonal is not all 0, I need to have done number 38 so I can refer to some values, but I'm just going to do it like this. So maybe some of them are 0, but let's just assume that the first one is not 0. So I'm going to put stars and asterisks. Asterisks? Whatever. So assume that the diagonal is not all 0, so let's just say that star here is not 0. Okay? So what happens is that A transpose is going to leave star alone. It's not going to do anything with star, but it's going to switch the rows and the columns. Right? So everything from the rows would go as columns, everything from the columns. So star would still be in the same spot, whether it be on the first 1-1 slot or in the 3-3 slot. As long as it's somewhere in the diagonal, star will remain the same. Now a negative A is going to change the signs for everything, right? It's going to make this into a negative star. And then whatever else, well, I can't put stars. Whatever else happens on the other side. Now, is there any chance at all for A transpose and negative A to be equal to each other? There's absolutely no chance for A transpose to equal negative A, since star, if it's not equal to 0, star will never equal to negative star. Only time that would work is that if star was equal to 0. And we assumed that at least one element in the diagonal is not equal to 0. So we assume that star is not equal to 0. So this is your contradiction. This is our symbol for contradiction. What? Oh yeah, so any math class that you might have had that requires proof, or if you're going to be a math major and you're going to have to take some proof classes, proof by contradiction is one of the common proofs techniques, and they use these weird symbols. Sometimes people go like this to make it quicker, so it still looks like two arrows bumping into each other. So this is your symbol for contradiction. Therefore, your assumption must have been false. Your assumption of diagonal is not equal to 0 must have been false. So that's how we do contradiction. What do you put after a proof again? What's the 3 letters? Okay. QED, quad eris demonstratum. All right. So that's your proof for showing skew symmetry. I think we took a little too much time on that. Now we're all skewed. All right, let's move on to our next section. Our next section allows us to solve for that problem AX is equal to I. And for that, we need an inverse. So let's define an inverse. They call it inverse, but I think more proper is that if we call it a multiplicative inverse. Now, we're not going to call it multiplicative inverse all the time because that's too many syllables. But that's what it really is. Multiplicative multiplicative. So an inverse, first of all, you need a square matrix. If A is a square matrix, then an inverse of the square matrix A is denoted by A with a -1 on it. And it has the property that if you multiply that with A on either side, now remember it's multiplication is not commutative, but in this case, if you multiply this on either side, then you're going to get your multiplicative identity, and your I is your multiplicative identity. So this is equivalent to, in terms of our real number language, 1 over x times x is equal to 1. X times 1 over x is equal to 1. Okay? Except that it's 1 over x business, we kind of don't know. Sometimes we write 1 over x, right? As x to the -1, so that's the inverse. That's your multiplicative inverse idea. But we can't write 1 over A when we're dealing with matrices because it doesn't make sense for us to divide matrices. So we have to think about this as multiplying by its inverse. All right. So this should have been a -1. So the primes get kind of messed up sometimes. Some textbooks use prime for the inverse, and some other places like MATLAB uses prime for the transpose. So you have to be careful with what it is you're dealing with and how they're defining the inverse versus the transpose. Those two are different things. So you have to be clear about what it is. So we'll use capital T for transpose when we're writing things down. And just remember that in MATLAB it's a prime, or it's a apostrophe. And then we'll use -1 for the inverse. All right, so if your inverse exists, this is if. Whoa, typos. Maybe I should make that correction now. If such an inverse exists, then A raised to the -1. Whoops. What? A raised to the -1. Okay, so a simple theorem here says that if you can, in fact, find your inverse, then that inverse is unique. There are no other inverses that you can find. That seems obvious, right? Is there a place where this might not be true? Is there a time when this is not true? I don't know. Yeah. Okay, maybe I should erase that. All right. So that's one important theorem that comes here. When you find an inverse, and that's the only inverse that would exist. And then another important part of the whole idea of introducing inverses is for us to be able to solve for equations involving matrices. So A is an invertible matrix, then the system of linear equations A, x plus b, you guys are familiar with that, has a unique solution, and its solution is A is equal to the inverse of A times B. I feel like we should come up with an example of this. So let's come up with an example of this. Let's see. Trying to come up with a really simple example. So let's come up with a system of linear equations. Let's say x plus y is equal to 4, x minus y is equal to what? 3, would that work? Does this work? Can you think of x and y as an answer already? All right, we'll go with this. So your system would look like this. It would be 1, 1, 1, negative 1 times xy, right? Think about the multiplication is equal to 4, 3. So that's your system of equations transferred, and now looks like a matrix equation. And this is your x vector over here. This is your b vector over here, and this is your matrix A. Okay? Now, we haven't talked about finding A inverse yet. I guess we should have talked about that first. But the idea is that if we find out what A inverse is equal to, and let me just find out what A inverse is equal to. What was the matrix again? 1, 1, 1, negative 1? 1, 1, 1, negative 1. Looks like it's 1/2 times 1, 1, negative 1. Wait, 1, 1, 1, negative 1. Right? All right, so we'll take that. So for now, we'll just say we got it from Wolfram alpha, but then we'll find a way to actually solve for this. So this is your inverse. According to this, your xy, your x vector, is actually equal to 1/2 times the matrix 1, 1, 1, negative 1 times a vector, or you can consider it as a column matrix, 4, 3. So you see the components here. This is your x matrix, or your x vector, is equal to your inverse times your B matrix. Okay? Now I can kind of consider this as a matrix multiplication, so I can multiply that 1/2 now or later. Remember one of those properties for matrix multiplication? You have a k times A times B. I can say k times a or k times b or k and then do a times b first. So let's work this out. I'm going to do the matrix multiplication, column or row and column. So 4 plus 3 is 7. 4 minus 3 is 1, right? Did I do that right? So it looks like my answer should have been 7 halves and 1 half. Well, that's not what I was thinking. Does that work? Seven halves plus 1 half. I thought this was an easy one. I thought we were going to get whole numbers. Oh well, is this correct? If I put x is 7 halves and y is 1 half, I'm going to get 3 and 4? Okay. I feel like I want to row reduce this just to make sure it's right. You can row reduce this to make sure it's right, right? Are you guys happy with this? I'm still not happy, but if you're happy, let's move on. If you're happy and you know it. Oh, I found the inverse? Wolfram alpha. But we'll show how we actually get the inverse in a minute. So yeah, finding this inverse now is going to be our next task. Okay, so that's this whole business. It's essentially changing your what do you call this? Your system of linear equations, solving for your system. Instead of doing this row reducing, if you have access to finding the inverse, you could just find the inverse and then multiply it times the augmented part, the augmented vector part. So it's the A inverse times B. Okay. All right, let's one more thing before we get to actually finding the inverse of at least a 2 by 2 matrix. And for that, it would be good if we knew the definition of a determinant of a 2 by 2 matrix, which we've done in various ways already. So here's just a quick definition. If you have a 2 by 2 matrix, the determinant is going to equal to essentially the diagonals, the product of the diagonals minus the product of the wings. So it's A times D minus B times C. Yeah. Not quite, but the cross product is kind of embedded. No, this is embedded in the cross product somehow. Yeah, so doing the cross product, if you guys have seen the cross product before, I have to assume that you haven't but if you have seen the cross product before, the cross product is finding the determinant of some weird setup of a 3 by 3 matrix. And so we're going to talk in detail about determinants later on in the future, but for right now we're just looking at determinants of a 2 by 2 matrix. And the determinant of 2 by 2 matrix is essentially the product of the diagonals minus the product of the wings. If the diagonal is a diagonal, and so the wings are just the other numbers aside from the diagonal in a 2 by 2 matrix. All right, so now that we know the determinant of a 2 by 2 matrix, we have a special formula for the inverse of a 2 by 2 matrix. And the inverse of a 2 by 2 matrix is given by first finding the determinant of your matrix and then doing something weird to the matrix itself. What did they do with the original matrix A, B, C, D to get this new matrix over here? They switched the diagonals and they negatived the wings. switch diagonals, and negative the wings. Okay? So now we know how to find the inverse of a 2 by 2 matrix. That 2 by 2 matrix that we were working on a page ago. I actually had to go to Wolfram Alpha to find the inverse of this matrix, right? So now let's see if Wolfram Alpha is correct. Of course they're correct. Let's see if I could do it so that it matches the answer. So first we need to find the determinant of A. Determinant of A is a product of the diagonals, 1 times negative 1 minus the product of the wings, 1 and 1. This turns out to be what? Negative 2? Positive 2. Negative 2, right? Negative 2. So that's your determinant. And so A inverse should equal to 1 over the determinant, which is negative 2, times, what do we have to do? We have to switch the diagonals. So the negative 1 and the positive 1 switched. Switch the diagonals, and then negative the wings. So I'll put a negative in front of both of these. Right there. Right? Well, to make this look like Wolfram Alpha's answer, I'll just take this negative and distribute the negative through, and I get this 1/2, 1, 1, 1, negative 1. And that's what Wolfram Alpha got. Or we could just multiply everything out. Positive 1/2, 1/2, 1/2, negative 1/2. So that's my inverse. Okay? So it turns out that if we have a 2 by 2 matrix, we can easily find the inverse. That's, yay, that's great. Now, when we start dealing with larger matrices, formulas aren't so simple anymore. But at least we got something for a 2 by 2. Good for starters. Okay, questions? All right. Some examples here that we don't have to do anymore because you guys are all experts on it. Before we try to find inverse of 3 by 3 matrices, let's see if we can lay out some general properties or theorems that involve the inverse. Okay, the first one says that if A is invertible, then you can find the inverse of the inverse, and the inverse of the inverse should be the original matrix. Okay, that's kind of looks like the transpose, huh? Okay, remember the inverse and transpose are not the same. So in this case, they just happen to have the same similar looking formula. All right. If you have a scalar multiple of a matrix, then the inverse of that is the inverse of the matrix times the inverse of the scalar. Now, the scalar is a real number. When we're talking about inverse of a real number, remember that's just the reciprocal. So, just like 1 over c. Now, here's another interesting fact. The inverse of a product is equal to the product of the inverses in reverse order. That's another one that looks like the transpose. But it's not the transpose. Okay? So this is an important fact. We'll dig deeper into this fact a little bit later on. But we'll use this quite a lot, the inverse of a product. And here now they're mixing up the inverse and the transpose. The inverse and the transpose are like inverse, not inverse, but they're commutable operations. You can take the transpose first and then the inverse, or you can take the inverse first and then the transpose. And then taking this to a power is the same thing. All right, these are all theorems, so they're supposed to be proof-worthy. Should be able to prove one or a couple of them. So I got my eye on either C or E. Interested in proving one of those? Which one should we do? C? Let's do C. All right, let's see if we could prove C. A, B, inverse. So let's prove this. Now, according to the definition, well, it's a definition of inverse anyways. I'm going to go back to the inverse. The definition says that if we multiply A times A inverse, we should get I, and then vice versa. Right? So this is a definition of the inverse. And usually when we're proving things, we don't have enough properties or theorems associated with it yet. We're always going to refer back to the definition. So this is how inverse is defined. So let's see. So that means this, what was the inverse again? A times A inverse? Okay. So let me write it like this. A times AB, that's supposed to be a B. Inverse should equal to I. Right? And AB inverse times AB should also equal to I. So let's see. A and B are all supposed to be invertible, right? So I could go from here and say A times B times AB inverse is equal to I. So I lifted the parentheses. And then what I'm going to do, this is the tricky part, is that I know that A inverse is supposed to exist. A and B are invertible, so I know that A inverse exists. So I can multiply this by A inverse on both sides. Now, this is really subtle, but what I just wrote down is not quite legal, not quite correct. What do I need to change in what I wrote down here in red for this to be correct? Any ideas? So you guys are living in a commutative world with the real numbers, but matrices don't commute. Nick, you want to give it a shot? What is it? What's wrong? No. A inverse needs to be in the front. That didn't work out so well. That wasn't as slick as I thought it was going to be. A inverse needs to be in the front. Okay? Since I'm multiplying the left-hand side by A inverse on the left, I have to multiply the right-hand side by A inverse on the left. Okay? So now we know that A times A inverse is the identity, and anything times the identity is itself. So my left-hand side should look just like B times this, and my right-hand side should look like A inverse without the identity, because it's itself. Right? Now I want to get rid of B, and for the same reason that I had this A inverse multiplying on the left side for both sides, I need to do the same thing for B. For that, I'm going to make a little bit of room here, and I want to multiply by B inverse on the left for both of them. Okay, this thing again disappears, so I just have A, B inverse is equal to, what do I have on the right hand side? B inverse times A inverse. Okay, and I can just QED this because I'm done. Okay? So that's an important property. When you take the inverse of something, you can't just take the inverse of them separately. You have to switch the order of the product. All right? Now, I'm just going to put this one more piece of information on in our notes. So the inverse of a product of invertible matrices is a product of their inverse and reverse order. So this statement over here says that if you have A times B, right? But if I had more, then the inverse of this whole product of things is just the product in reverse order. So this would be E inverse times D inverse times C inverse times B inverse times A inverse. And then this last statement over here says that if A, B, C, D, and E were all the same, A, then they're all the same matrices, so they could just be combined into any of these things. All right, this piece of information over here, where we take the product of a whole bunch of matrices that we're multiplying together, will come up important in the very next part of this section when we examine, they call them elementary matrices. So next time we'll define elementary matrices and what they have to do with whatever it is that we're dealing with. We're continuing to find inverse of matrices for larger matrices. We don't want to restrict ourselves to just 2 by 2, right? We want to be able to do this for a 3 by 3, 4 by 4, etc. And for that, we're going to introduce ourselves to elementary matrices. That'll be for next time. All right, see you guys.